Okay, in this video we're going to start talking about inverse trigonometry. Now, inverse trigonometry deals with inverse trig functions. So in order to understand how these functions work, we really need to kind of know about inverse functions. I've got a video on that. You should check it out. Okay, so refresher about what we know about inverse functions. Okay, inverse functions, the domain and the range are switched between a function and its inverse function. Okay, that also means that the inputs and the outputs are switched. So x values become y values become x values. Graphically, they are reflections about each other. They reflect reflections of each other about the line y equals x. Okay, and this is important that inverse functions still need to be functions. Otherwise, they wouldn't be functions. And so, in order to create an inverse function from a function that is not what's called a one-to-one function, we need to have a domain restriction on our original function. Real quick refresher, what is a one-to-one function? A one-to-one function is a function where every input has just one output. That's what a normal function has. But also that every output has just a single input. Okay, it passes both the vertical and the horizontal line tests. And then lastly, and this part's also very important too, is that the composite of a function, the compound function of f inverse of x, so a function, hopefully this makes sense, it equals x once you plug in an inverse function into the original function, and vice versa. Okay, so this is y equals sine of x. Now, we have an input and an output to this function. The input to a trig function is always an angle. The output is always a ratio of side lengths. Now, specifically for sine, right, sine of x or sine of theta is equal to the opposite side of that angle divided by the hypotenuse, right? So specifically, it is the ratio of side lengths that's the opposite over hypotenuse. But we're just defining the kind of thing that the output is. In this case, it's the ratio of side lengths. So, if we had the inverse sine to the -1 is this notation. Now, you should know that another way to write this would be y equals arcsine of x. Okay, arcsine of x is kind of the way, if you're into programming at all, arcsine is kind of preferred to the -1 kind of notation there in the superscript, because we can't really do that very well in programming and syntax. So we have arcsine as the function. It's the exact same thing. Okay, this is literally the same thing as this. All right, so if you see either of those, just know they're the same. So now we flip what was the input and the output. So now the input to an inverse trig function is just a ratio of side lengths. In the case of sine, it would be the opposite side divided by the hypotenuse. Okay, and then the output to an inverse trig function is an angle. And this is always the case. I can't stress how important this is, especially as we move further and further into trigonometry. Whatever is inside of the parentheses of a trig function, it's just an angle. No matter how gross and disgusting it looks, it's just an angle. Okay, same thing if for an inverse trig function, and this applies to all inverse trig functions, not just inverse sine or arcsine, but all of them. Whatever's inside the parentheses, it's called the argument, whatever's inside the parentheses of that function is just a ratio of side lengths. I promise you it's going to look at times like what's inside there is the farthest thing from a ratio of side lengths, but it is. That's what it is, okay? Just remember that. All right, now, let's look at y equals sine of x specifically. You should know right away, something you should note right away is that y equals sine of x is not a one-to-one function because it fails the horizontal line test horribly. Okay, it would literally fail it infinitely many times. So what do we have to do to restrict the domain of this function to make it a one-to-one function? Another way to think of that is what section of the period, or like what part of the domain of y equals sine of x can we use that will represent every part of the range. And for sine, the simplest part of it is from right here to right here. So from -pi/2 to pi/2, including -pi/2 and pi/2, because the range is important, right? It's 1 and -1. That's the range of y equals sine of x. So we restrict the domain of y equals sine of x in order to get the inverse function, and what we end up with is this. So there's our domain restriction. And we know from talking about inverses that the domain of a function is the range of its inverse function, and the range of a function is the domain of its inverse function. This might not seem super important, but it will be, I promise. Okay, now let's look at cosine. Okay, here's cosine of x. I'm going to ask ourselves the same question. What would be the easiest part of the domain of cosine for us to cut out of it to make it so that all of the possible values in the range are represented? To me, it looks like I need to go from 1 to -1, so I'm going to take this section of it, okay? And I still want -1 and 1. That's part of the range. So what we end up with is this. Okay, the domain of, if we restrict the domain of cosine from between 0 and pi, 0 and 180 degrees, we will be able to get all the parts of the range. And again, right, the domain of a function is the range of the inverse, and the range of the function is the domain to the inverse. Right, what about tangent? So tangent is actually pretty clear here, right? The domain of this function is really weird to begin with, but it turns out that there's a really nice little section of it that will represent all of the range, right? It's just this part. Okay, that part will give us the entire range. And it's 1 to 1, so we're good. So that's going to be the part of the domain of tangent that we care about. So it's from -pi/2 to pi/2, but not including either of those, because there's vertical asymptotes on the graph of tangent here, right? So it's everywhere from -pi/2 to pi/2, not including either. In other words, it's this. Okay, and we would expect the range to be what it is. It's everything, right? So again, and this part's kind of weird because the domain of our inverse function is actually everything. It's all real numbers, which is a little bit strange for us when we think about tangent, because we know tangent has all these gaps in it. But when you lay tangent on its side, kind of, well, now you have all real numbers. Okay, so here's a table that represents the domain and range of all of the trig functions. Just didn't go through the process for cosecant, secant, and cotangent, but those are the values right there. And I'm gonna show you a graph of these things. Okay, so I've got the line y equals x on there because that's one thing we know about inverse functions, is that a function and its inverse are reflections of each other about the line y equals x. So look at sine and arcsine. Notice arcsine because Desmos accepts arcsine as the inverse sine function. You can see that it's just these little sections of sine here. Like, you can imagine sine would keep going on and on and on. I can't draw it on here, but it would just keep doing that. And then that's arcsine. Let's turn those off. Let's look at cosine. Okay, cosine, we restricted it between 0 and pi. So arc cosine, a reflection about the line, does this weird looking thing. Okay, this is all for a reason, I promise. Here's tangent. That's the section of tangent we took. So if we flip that, that looks like that. Okay, secant is, this is the section of secant that we would take. It's everywhere from 0 to pi, not including pi/2. And then we flip that, it's that. So that's kind of crazy. And then this one looks pretty weird too. Actually, if you turn them all on, you get a pretty cool pattern. Not a pattern, you get just kind of a cool shape here. But it's all kinds of craziness going on there. So those are the restricted domain trig functions and their inverse functions. All right, so what does this mean for us? Well, this allows us to, if we were given the ratio of side lengths of a triangle, we can use inverse trig to get what the angle is. Now, you're used to doing this just by pushing buttons on your calculator, but it's important to know that there are certain values that will never come out of an inverse trig function, and there are certain values you cannot plug in to an inverse trig function because of these domain restrictions. So let's look at some of that stuff here. Okay, first of all, when you're trying to do an inverse trig function by hand, it's good to think of it this way, right? This question is asking the sine of what angle gives me what that ratio of side lengths is, right? So we can also draw a triangle, and we'll do that in a second. So, for example, cosine of what angle gives me 1? Well, you should think to yourself, okay, cosine of 0 gives me a value of 1. So this is 0, right? Now, there's another angle for cosine that gives me 1, right? Because cosine of 0 is equal to 1, right? But cosine of 2 pi is also equal to 1. But I don't want to get a value of 2 pi out here. if I did that, if I could get either of these values out by putting in a 1, now it's not a function. A function only has one output for a given input, okay? So that's why we had to restrict the domain, right? When we cannot plug in, well, you can plug in 1, you can't plug in like 2 into cosine, because there's no ratio of side lengths of 2 for cosine. It doesn't make sense. It's outside of the domain of the inverse cosine function because it's outside of the range of the normal cosine function, right? We have to restrict the domain because we can't get different answers out from doing an inverse trig function. Okay, let's look at another one. Hey, sine of what angle gives me positive 1/2? So we can think about this too as a triangle, right? 1/2. All right. Well, that means that the opposite side would need to be 1/2, and the adjacent would need to be 1. Hey, look, this is an angle right here that I know from the unit circle because this is root 3 over 2. I know that this is 30 degrees. The sine of what angle gives me 1/2? 30 degrees, or, in preferable way, pi over 6. Now, why is it not? Because over here, too, is also, this angle here would also give me an output of sine of 1/2. So sine of this angle also gives me 1/2. Well, how come it's not that answer? Because we can't have multiple answers that could come out of the inverse sine function. It's just the one in the domain that we restricted, okay? Well, just the one is in the domain of our original function, which we said for sine was basically it was from negative pi over 2 to pi over 2, right? So, and it has to be in those two quadrants. All right, tangent of what angle gives me positive root 3 divided by 3. Now remember, tangent is always tangent of 30 degree and 60 degree angles are either root 3 or root 3 over 3. It's the 30 degree angles, the pi over 6's, that give me the root 3 over 3. So this is just positive pi over 6. Tangent, so another way to think of this would be the tangent of pi over 6 is equal to positive root 3 over 3. Now, of course, there are other values of tangent. Tangent of, for example, tangent of 7 pi over 6 is also root 3 over 3, but this is outside of the domain of the tangent that we restricted, which means it's outside of the range. It's outside of the range of the inverse tangent, so it could never come out of the inverse tangent function. It could only be this. Okay. Sine of what angle gives me negative 1/2? You should know right away this is negative pi over 6 it's going to be. Okay, that is not the same thing as 11 pi over 6. I know that that's the same angle, but your calculator will not give you 11 pi over 6 because 11 pi over 6 is not part of the range of the inverse sine function, just like it's not part of the domain of the normal sine function when we restrict it to get the inverse sine function. Okay, so this is negative pi over 6. And why is it not 7 pi over 6 or 11 pi over 6? Again, it can only one thing can come out. Okay, tangent inverse of the tangent of 2 pi over 5. What is this? Remember, this is just a ratio of side lengths, right? So tangent of what angle gives me the side lengths of tangent of 2 pi over 5? Like, that's kind of a weird question, right? So what tangent of what angle gives me the side lengths of the tangent of 2 pi over 5? The tangent of 2 pi over 5 gives me these side lengths. Another way to think of this is this. Remember we said that f of f inverse of x is equal to x, or f inverse of f of x is equal to x? Yeah, right? So it's just this thing, right? So it's just 2 pi over 6. You can think of it. Now, it's a little bit dangerous to think of it this way, and you'll see that moving forward. But it's you can think of it as this tangent inverse and this tangent. They kind of cancel each other out. Okay, that is what's happening, kind of. All right, let's move on. So what would this be, given what we talked about in the previous problem? Well, this would just be pi over 10, and this is fine because pi over 10 is part of the range of the inverse cosine function, just like it's part of the domain of the normal cosine function when we have our restriction on there. So this is fine, but you gotta watch out for that. If it's not part of it, we have an issue. Okay, these ones are a little bit switched now, right? I don't have the inverse cosine on the outside, but I do have right here is an angle. Okay, this is just theta. So cosine of theta is going to equal what? Cosine of theta is going to equal negative 0.7. Okay, this is the same deal. Where we can just take essentially they cancel each other out. And this is okay because negative 0.7 can be is part of the range of normal cosine, right? Remember, normal cosine is between negative 1 and 1, the range of it, so this is within it, so we're good. Okay, it's all fine. And additionally, this negative 0.7 is part of the domain of our inverse cosine function. So that's still good. Everything checks out. We're good. Here's another one. Okay, sine inverse of sine of 2 pi over 3. Okay, so you would think right away that this was 2 pi over 3, right? And you would be wrong because 2 pi over 3 is not part of the range of the inverse sine function. Remember, the inverse sine function has a range from negative pi over 2 to, negative pi over 2 to pi over 2. And so this 2 pi over 3 is not part of it, but there's another value, there's another, remember, this is just a ratio of side lengths, right? And so this ratio of side lengths, in fact, we know what this is, right? We're trying to think what this is real quick. Hold on. It is root 3 over 2, right? So maybe we'll just say, all right, sine inverse of root 3 over 2. Okay. Oh, well, that happens at pi over 3, positive. And pi over 3 is part of the domain, is part of the range of inverse sine, just like it's part of the domain of a normal sine function that's been restricted. Okay, so you got to be careful here. It's very tempting to want to say it's just this because of how we said that these things cancel each other out, but you have to make sure that it's part of the range, and in this case it wasn't, so we have to go back to where the equivalent value, essentially. Okay, find the exact value of cosine inverse of 2. Okay, so it's just 2, right? No, it's not 2, because this here is an error. You can't plug this in. Think about what this means, right? If we had any triangle, okay, and we said that's theta, and we said the adjacent side was something, and in order for cosine to be 2, in order for the ratio of the adjacent side divided by the hypotenuse to be 2, this would have to be 1/2. That should raise some red flags for you right away because the hypotenuse is always the longest side of a right triangle. So this could never work. 2 is not part of the domain of inverse cosine, and so this whole thing is just undefined. Okay, it cannot work this way. All right, the last thing I want to do is draw you a quick picture here. Okay, and this picture is going to be really useful when it comes to your thinking about how these functions work. Okay, so here is I'm going to draw kind of a unit circle here. Just a circle. It's not going to be very good. But what we're going to do is we're going to say that green is a sine inverse of x, or arcsine of x. Okay, this is the range of this function. It can be anywhere from negative pi over 2 to pi over 2. Okay, so if I'm using inverse sine, the answer that comes out could only be part of this green. Okay, now let's do another color. So let's say inverse cosine of x is going to be, remember what we said for this, it's everywhere from 0 to pi. Okay, including. So those solid dots mean including. Oh, sorry, that should have been green. I'm going to have to fix that somehow. That's green. Okay, and then lastly, we'll just do this for tangent because these are the ones that are going to come up the most. Let's do blue for tangent. Okay, tangent of x. Okay, the way this one works is, remember, it's everywhere from negative pi over 2, not including it, all the way to positive pi over 2, not including it. So the only values that could ever come out of inverse tangent are those values. This is screenshot worthy right here. This is something to keep handy. This is something that if we were in the classroom, it would be written on the board for your reference. It's something that will help you not run into the issue of this problem right here, right? It can't be 2 pi over 3 because I'm doing inverse sine, right? And inverse sine, 2 pi over 3 is over here, right? Inverse sine is green, so it's not going to work. I need to look for what was the equivalent value. Oh, it's that one, which was positive pi over 3. Okay, I hope I can easily erase those lines. Yeah, I can. Okay, so I would screenshot that if I were you, but it's useful to have. And that's kind of the entire gist of inverse trig. Now there's more to it, but it's just incremental. It's incremental, and we'll handle it. We'll take it as it comes.